All right, so we stopped in the middle of proving this theorem, 6.24. We were talking about orthogonal projections, and just to remind, an operator T is called an orthogonal projection, provided that it is a projection. Provided that it is a projection, so T equals T squared, that's something we proved is equivalent to that. And more than that, those two heavily underlined things here hold. So the orthogonal complement of the range of T is the null space and backwards. And we're in the middle of proving that orthogonal projection is equivalent to T equals T star and equals T squared. So we're going in this direction. Well, no, actually we're here. Already proved the first half, the first implication. So if T is an orthogonal projection, then T equals T star equals T squared. So now we're going backwards. We're assuming that this holds. And we're trying to show it is an orthogonal projection, which means projection and those two conditions with the range and the null. Now, because T equals T squared, then it's automatically a projection. So to be orthogonal, there are those two things that need to be proved. 1 and 2 there. So we are in the middle of proving the first, and we do this by double inclusion. So we started with an element X in the set on the right, in R of T, and we want to show that it belongs to the set on the left, which means X has to be orthogonal to anything in the null space. So we took the inner product between X and something in the null space, Y. But then because X is in the range, then X can be written as some T of Z. So we replace it by T between T of Z and Y is T star of Z and Y, because T equals T star by assumption here. Here's the assumption. Up there. So T of Z equals T star of Z, then move T in the other component. So you get the inner product between Z and T of Y. But because Y is in the null space, T of Y is 0, right? So in the end, the inner product between X and Y is 0, which is exactly what we needed. So this is one implication. So let's go backwards. So we need to show that the orthogonal complement of the null space is a subset of the range. Okay, so let Y be an element in the orthogonal complement of the null space. We want to show the range, but what does that mean? Remember that T is a projection. We've already seen that because T equals T squared by assumption. Being a projection, remember that the space V can be written as the direct sum between the range and the null space. And we've seen that T is a projection onto the range of T, right? So because T is a range, being in the range is equivalent to T of Y equals Y, because projection onto the first space, right? When you apply T to that element, it just gives you the part from R of T. So Y belonging to R of T is equivalent to T of Y being equal to Y. So this is what we need, that T of Y equals Y. And in order to get there, we're going to look at the norm of Y minus T of Y squared. We're trying to show that this norm is 0, of course. If we show that this is 0, then Y would have to be equal to T of Y, so Y is in the range, and we're done. So this is the inner product between y minus t of y and y minus t of y, which is the inner product between y and the right-hand side minus the inner product between t of y and the right-hand side. All right, so let's not forget, we're going to show that both of them are 0, those two inner products. So let's not forget where y is coming from. Y is in the orthogonal complement of the null space. So the inner product between y and anything in the null space is 0. So if we can show that this guy here is in the null space, then the first inner product will be 0. To be in the null space means I need to apply t to it and get 0. But t is linear, so this is t of y minus t squared of y. Remember our assumption, t equals t star equals t squared, so this is 0. So this guy here belongs to the null space of t. So the first inner product is 0. So we end up with the inner product, negative inner product between t of y and y minus t of y. The first one is 0. All right, it was a difference of two inner products. We proved that the first one was 0. So now we're looking at the second one. I'm going to move t into the second component. But again, t equals t star by assumption. So replace t star by t, and this is something that we've already seen has to be 0. So everything is 0. Therefore, y equals t of y, so it belongs to the range of t. All right, so what have we proved? We proved this first identity here, number 1. Number 2 will be very, very similar, so I'm just going to skip that. All right, so you just go both directions, both inclusions with the same idea. So let's move on. So we now have a characterization of what an orthogonal projection is, basically. T, that's all you have to check, that it's self-adjoint and that t equals t squared. All right, so the last idea in this section is the spectral decomposition theorem. It says the following thing. So you have a linear operator with eigenvalues, but you just pick one of each, right? So if they have multiplicities, you just pick one of each. So those are the distinct ones, lambda 1 to lambda k. Now, t is normal. Okay. T is normal if f is c, or t is self-adjoint if f is r. That is the assumption. What does that mean? What does this imply? Remember that we showed that being normal on C or being self-adjoint on R implies diagonalizability, right? So there exists a basis of eigenvectors for B. So these assumptions, both of them imply the same thing. So then Wi is the eigenspace corresponding to the eigenvalue lambda I. And then Ti is the orthogonal projection on Wi. And the points are true. So let's talk about each of them. So what does A actually say? Again, because T is normal or self-adjoint, that automatically means that T is diagonal. There exists an orthonormal basis of eigenvectors for V. All right, but let's go back a little bit to chapter chapter 5, I think it was, the one with diagonalizability. If you remember, when we constructed this orthonormal basis of eigenvectors, how did we do that? We went into each eigenspace, right, when a matrix or operator was diagonalizable, right? You took an eigenvalue, went to the eigenspace, picked a basis, right, took a basis from that eigenspace, and then do this for every eigenvalue and put them all together, right? And that's how we got the basis. So it's for W1, then one for W2, and so on, one for WK. All those spaces are disjoint, so there are no eigenvectors for the same eigenvalue, so the intersections are just 0, right? And in case that with an inner product, we've seen that already, that the eigenspaces are actually orthogonal. So if you take an eigenvector for an eigenvalue and another one for a different eigenvalue, then their inner product has to be 0. We proved that already. So A is nothing more than, you know, restating what we've already seen about you know, how to construct the basis for the basis formed by eigenvectors. I'm not going to go into details about B, but B basically says that if you pick one of them, if you fix one of them, and you want to find the orthogonal complement of it, like, you know, just to make it easier to write, let me just say I'm looking at the orthogonal complement of the first W there. And the orthogonal complement is going to be the remaining W's. So it's going to be W2 plus W3 plus WK. Right? So basically the sum of the other ones will be the orthogonal complement of each one of them. So I want to look more into parts C, D, and E, because those are actually here. So the idea is that you can actually take T, the operator T, and split it into a sum of orthogonal projections. So the main thing of this theorem is part E here. So write T as a sum, a linear combination, if you want, of orthogonal projections. So let's see how that works. Let's start with T, with part C. So Tij. Apply that to some element x in V. Okay. Well, x being an element in V can be written according to this external, to that you know, direct sum as x1 plus x2 plus xk, right? Each of them belonging to the corresponding Wi. And then Tj is the orthogonal projection onto Wj. So what will happen when you apply Tj to this x? What do you keep out of it? You just take the projection onto Wj, you just keep that part from Wj. So Tj of x will be xj. But now Ti comes, which is the orthogonal projection onto Wi, and you apply that to something that is in Wj, what happens? Well, unless I equals j, you're going to get 0, because Wi and Wj are common, right? So this is just be delta ij, right, the Kronecker symbol, which is 1 when I equals j and 0 otherwise, times xi, right? When I equals j, you just get xi. But xi is Ti of x. And that's exactly what part C says. Now Tij is in fact delta ij Ti. All right, part D. The identity itself can be broken into the sum of the k orthogonal projections, and the idea is the same as in part C, because when you apply the identity to x, you just get x, and x is x1 plus x2 plus xk, right? So the sum of all those pieces from the k orthogonal spaces there, x to xk. But x1 is in fact t1 of x because it's the projection, right? t1 is the first one, so t1 of x is x1. t2 of x is x2. tk of x is xk. So identity is t1 plus t2 plus tk. Okay. And finally, what I was saying is the main thing here, the spectral decomposition, part E. So you want to show that t of x is lambda 1 t1 of x plus lambda k tk of x. All right, so let's see t of x. This is what we need. T of x is, well, x is x1 plus xk, so t of x is t of x1 plus t of x2 plus t of xk. All right, but x1 is in W1. Who was W1? It was the eigenspace corresponding to lambda 1. So this x1 is in fact an eigenvector for lambda 1. So t of x1 is lambda 1. T of x2 comes from the eigenspace of lambda 2. So this is lambda 2 x plus lambda k x k. All right, but x1 is the same as t1 of x because t1 was the orthogonal projection onto the first space. So t1 just retains the first piece, right, from x, which is x1. t2 projection onto the second space. So t2 of x is x2 and so on. Basically, that was exactly what we needed. So let's see how to use this idea to show two things that we kind of seen before, but we're going to restate them now. Corollary 1. On a complex inner product space V, then an operator T is unitary. Remember that unitary means this. The norm of T of x is the norm of x for every x in V. And that was equivalent. There was a theorem with several things that were equivalent. One was that T star T equals T equals identity. So it was more than normal, right? Normal plus something else. So unitary, if and only. So we're going to restate that something else now. So T normal. And all the eigenvalues have absolute value 1. So we've seen this idea before, but now the proof is going to be much simpler using the spectral decomposition. So here's how it goes. Well, one direction will be the same as before, because if you assume that T is unitary, then according to that theorem that I already mentioned, T is normal, right? And more than that, since the norm, if lambda is an eigenvalue, and x is an eigenvector for lambda, then by being unitary, that means first x is the norm of x. But since x is an eigenvector, t of x is lambda x. A scalar, you pull it out of the norm in absolute value, right? So absolute value of lambda times the norm of x of x. X is an eigenvector, so it cannot be 0. So the only way in which this can happen is if the eigenvalue has absolute value 1. Okay, so we've seen this idea before. I'm still not using the spectral decomposition. I'm going to use it for going backwards. So if you assume that t is normal and every eigenvalue has absolute value 1, so that t is unitary. Okay. Unitary, again, is something that we proved is equivalent to this. First part is clearly satisfied by being no need to check the equality with the identity matrix. All right, so let's look at T star T. I'll go back to the spectral decomposition a bit. On a complex inner product space, so the theorem works. I'm going to use the spectral decomposition for T. I'm just going to replace it by lambda 1 T1 plus lambda K Tk. So that is T, so I need T star times T. The adjoint behaves nicely, right, with respect to taking a sum. If you have a scalar, it's going to make it, you're going to take the complex conjugate. All right, but T1 through Tk were orthogonal projections. And we've seen that an orthogonal projection means being equal to its adjoint in particular, right? So being self-adjoint. So I'm going to replace T1 through Tk star by T1 through Tk. Okay, so what happens now? Well, theoretically, I have to start distributing everything, right? But what happens, so if I distribute, I just look at those absolute value of lambda 1 squared times T1 squared, right? But what happens when I take this first one and the second one that comes here? So I do lambda 1 bar T1 composition with lambda 2 T2. Well, then I get T1 T2 composition. This is the main thing that I'm going to use. When you compose two of them, when I is different from J, what do you get? 0, right? Because you have the chronicle symbol in there, the delta ij. So T1, T2 is going to be 0. Same for T1, T3 and everything else, right? So all I'm going to keep from here are the ones that are, so I'm just going to multiply like term by term like this, lambda 2 squared, T2 squared. They are orthogonal projections, and orthogonal projections we've seen are equivalent. So T is an orthogonal projection if and only if T equals T star equals T squared. So all those T1 through Tk, T1 through Tk are all orthogonal projections. So tk squared. From the spectral decomposition. Well, being an it's the first theorem that we proved today, that an orthogonal projection has the property that is self-adjoint, the one before the spectral theorem. And now I'm going to use the same theorem, so this one here, which is 6.24, right? This result here about orthogonal projections. So T1 squared equals T1, again, because it's an orthogonal projection. All right, but here is the second assumption that we have. Every eigenvalue has absolute value 1. So I'm going to just replace them all by 1. So T1 plus T2 plus so on plus Tk, what was that? The sum of all those orthogonal projections is part D of the spectral decomposition is just the identity operator. T star T is the identity. Now you can imagine, well, I don't have to do the other one because T star T equals T star anyways. Yes?
I have a stupid question.
No
If the eigenvalue is 1, what is it actually doing then?
It's not 1, it's 1 in absolute value. Those are complex numbers. There are infinitely many things that could make this possible. Okay?
Thank you.
Mm-hmm. Okay. So corollary, the connection be self-adjoint now. So if the field is C again, and T is normal, remember that being self-adjoint implies that it's normal, right? So self-adjoint is stronger than normal, but how much stronger? T is being, so T is assumed to be normal, then T is self-adjoint. If and only if every eigenvalue is real. So basically, let's say you have a normal operator, and you're wondering if the much stronger condition being self-adjoint is check the eigenvalues. If they're all real, you're done. It's much stronger than normal is self-adjoint. So let's see. So again, we've seen this implication before. Let's go through it. It's just one line. Being self-adjoint, T equals T star, right? So if lambda is an eigenvalue, and let's say x is an eigenvector corresponding to this lambda, then one thing about normal operators was this property here that TR had the same eigenvectors, but the corresponding eigenvalues were the complex conjugates. But because T is assumed to be more than normal, so self-adjoint, T star of x is the same as T of x. And T of x, because x is an eigenvector, is lambda x. So lambda x equals complex conjugate of lambda times x. X is an eigenvector, so non-zero. So the only way to make this work is when lambda equals its complex conjugate, and that's only true for real numbers. So if it's normal, then it's self-adjoint, and self-adjoint, then every eigenvalue is real. Let's go backwards. So let's just assume now that T is normal and that every eigenvalue is real. We want to show that T is self-adjoint. All right. Go to the spectral decomposition theorem. because T is normal. Again, the theorem works, right? So T is lambda 1 T1 plus lambda K Tk. So T star is the adjoint of that sum, but the adjoint will look like this. We're assuming that all the eigenvalues are real, which means the complex conjugates will not do anything, will not change anything. And finally, again, T1 through Tk are orthogonal projections, so they are, in particular, self-adjoint. And this is nothing more than the original. How?
If it was an orthogonal projection,
But T itself, that's the idea. That's exactly the idea what you said about the spectral decomposition theorem. T itself is not an orthogonal projection. Right? T is just any operator that is normal. Okay? Any normal operator, according to the spectral decomposition theorem, can be written as a linear combination of orthogonal projections, even if itself is not, because yeah, if T itself is an orthogonal projection, then it's automatically self-adjoint, but in general it's not, right? But still you can connect it to the idea of orthogonal projections through that linear combination and the spectral theorem. And that's a really useful, I would say, technical result, because it makes those proofs pretty easy to deal with. Okay. All right, let's move to something more serious, I would say, the singular value decomposition. So there are two main ideas that we still need to cover, and that's what I'll concentrate remaining 4 lectures, three other than today. Singular value decomposition theorem and the Jordan canonical forms for matrices. So let's start with a singular value theorem for linear transformations first. So we're in 6.7. And we'll go through the proof, but as you look at the statement, it might become already a bit confusing. It's a very long statement with a lot of things in there, so let's go slowly through it. So you have a linear transformation from a finite dimensional inner product, another one, finite dimensional as well, W. T has rank R. The rank is the right dimension of the range of T. Then the theorem says the following thing. There exist orthonormal bases, one for V, one for W. So V1 through Vn is an orthonormal basis for V. U1 through Um is an orthonormal W. It's assumed, of course, that the dimension of V is n, dimension of W is m. Right? So it's going from an n-dimensional vector space into an m-dimensional one. Okay, and there also exist positive scalars. Those scalars will be called the singular values of the operator T. With this property here that, well, you see how many there are? Non-zero exactly R. What was R? The dimension of the range of T, right, or the rank of T. So for each of those non-zero scalars, T of Vi is lambda I Ui, right? So you're moving Vi from the first space into the second space where the basis was Ui. So T of Vi, sorry, not lambda, sigma I Ui. again, up to R, from 1 to they are arranged in decreasing order, right? So sigma R is the smallest number, positive number. From R plus 1 on, they are all 0, right? Everything else, if anything is left, will all be 0. And that's where T of VI will also be defined to be 0. The second part of the theorem says that the scalars, so the singular values, basically, are uniquely determined for T, so there is just no way to find another set of such numbers with the same properties as above. However, the second part here actually says a bit more. It kind of tells us how to numbers. Right, exactly in that last line that I highlighted, that says that the operator T star T has the eigenvalues given by the squares of those sigma i's, and VI's will be the corresponding eigenvectors, right? So it kind of tells you where to go. So basically the idea is the following. You're given an operator, you compute this operator T star T, you find its eigenvalues, take the square roots, that will be your singular values for T, and the eigenvectors will be the basis for the first space. But, you know, that's, you know, the shortcut, let's say. Let's go into the proof, and then we'll try to apply it. Okay. So, again, the key is in the operator T star T. T star T goes from, well, T goes from V to W. T star goes from W to V. T star T will be a linear operator on V, which is normal. Why is it normal? Well, let's check that. An operator is normal. An operator U is normal if U star U equals U star, right? U is T star T for us. So, apply the adjoint to the first one. What do you get? You get, it switches the order, right? You get T star star, which is T. And then another T star and another T. And on the right side, you have T star T already. And then when you apply the adjoint to the second group, you get T star star, which is T again. Okay, so T star T is an operator that is normal on V, right? Therefore, yeah, well, what I'm trying to say now is I'm going to argue that T star T, so V should have an orthonormal basis of eigenvectors for T star T. However, from being normal, I would need V to be a complex space, right? Actually, I need more than that, and more than that is also true. It's also self-adjoint. The adjoint of T star T is T star star, which is T. So now, is enough. We went through this argument before. It doesn't matter if the space is real or complex anymore, because being complex and normal implies the existence of the orthonormal basis of eigenvectors. Being real and self-adjoint implies the same thing. So now we have them both. So in conclusion, no matter whether V is complex, there exist V1, V2 through Vn, orthonormal basis for V consisting of eigenvectors for T star T. Let's say the corresponding eigenvalues are let's put them in decreasing order. And by the way, I'm allowed to put them in decreasing order because they are real numbers, right? T star T is self-adjoint, and we just proved it was corollary to there. Any self-adjoint operator has real eigenvalues only, right? If they were complex, I couldn't arrange them in increasing or decreasing order. But anyways, they are real and positive. Being so, let's say so the first R of the positive. So let's work with those now. I want to define those six. So what have we got so far? We got this basis, right? V1 through Vn, orthonormal basis for V. We're going to define sigma 1 through sigma r as being the square roots of those eigenvalues. And we're going to, so we got the sigmas, right? We got those. So now we only need to find this basis here, right? But this basis cannot be arbitrary, the basis for W. It has to be connected to V through this equality here. So we're just going to define Uy to be 1 over sigma I T of Vy. So this identity holds. Now, those vectors Ui will, of course, be in the image of T, which is in W, right? But I don't know that they will form. What do I need them to form? They need to form an orthonormal basis, right, for W. And I don't know that. So let's just check that this set is an orthonormal set. I might not have enough vectors to get a basis because the dimension of W is M, right? So I'm not trying to check that U1 through UR will form an orthonormal basis. I just want to check that those R vectors are forming an orthonormal set. So I'm going to look at the inner product between two of them, Ui and Uj, and I'm trying to get delta Ij, right, the Kronecker symbol. I want it to be 0 if I and j are different. I want it to be 1 if they are the same to give me unit vectors. Again, I is between 1, I and j are between 1 and r. All right, so Ui is 1 over sigma I T of the I. Uj is 1 over sigma j T of Vj. Sigma I and sigma j were the square roots of those real number 1 through lambda r, so we just go out in, of the inner product as they are, which again over sigma I, sigma j, inner product between T of Vi and T of Vj. But everything came from T star T, so let me come up with T star T. So move the t from the second component into the first, so t star t of vi vj. All right. The vectors vi were eigenvectors for t star t. So t star t of vi is lambda I vi. Inner product of vj. And then pull out lambda I. So we get lambda I over sigma j times the inner product between vi and vj. The vectors v1 through vn formed an orthonormal basis for v, so they are orthonormal, form an orthonormal set, so this is delta ij. So we automatically get 0 if I and j are equal, right? But when I and j are equal, what do we get? We get lambda I over sigma I times sigma I, so sigma I squared. And remember how we define sigma I? To be exactly the square root of lambda I. So this whole thing turns into 1. So delta ij as needed, right? So U1 through UR form an orthonormal set in W. W which had dimension n, m. So R vectors might not be enough, right? Being orthonormal, they are orthogonal, so linearly independent, right? So you have a linearly independent set of R vectors. You can always expand that to a basis. You can extend it to an orthonormal basis because the set is already orthonormal. So when you go through the Gram-Schmidt, you will not change the first R vectors, right? You will just change the remaining ones that you're adding. So what I'm doing here is not just trying to, just go through the proof for proving it. This is actually what you have to do in all the examples. So this kind of arguments here will tell you what to do and how to compute the eigenvalues and those bases. All right, so at this point, we're actually done. So we found an orthonormal basis for V. We found one for W that is connected through that, right, with T. And we found our set of singular values, sigma 1 for sigma R. Okay. So now, of course, we made use of this idea here at the end. That's the real key of this singular value decomposition. But anyways, this proof doesn't do anything unless you're really working an example. So let's just see how it actually works out. Well, let's start with we might have time to do two of them. Let's see. This is 2A in this section in the book. We're going from R2 to R3. And the operator is the following. Find the singular values of T and the orthonormal basis from the singular value decomposition for R2 and R3. Singular value decomposition, by the way, is usually called SVD. So I was telling you that this is one of the most important concepts, I would say, in linear algebra, and I will give you more examples probably next time. But even in applications in general, in image processing, and there are so many directions in which the singular values are used. The main idea being that this set of numbers, right, is just a set of numbers, are numbers, right, associated to a linear transformation or to a matrix, we'll see later on in this section, retains so much information about that matrix that for storage purposes on computers, for instance, right, it's essential from a large data to retain just a couple things that tell you a lot about the original structure. And that's why image processing, for instance, and I'm going to show you some examples of, like large-scale images stored in the computer using just the singular values of the associated matrix, and to see the difference that is just a slight difference between the two images. So we'll look into that next time. But let's just try to see how to compute them first. All right, so this is V, and this is W, right? V has dimension 2, W has dimension 3. What are we actually looking for? What do we need to find? We need to find the singular values, right? We need to find an orthonormal basis for V. Those are the V's in the theorem. Orthonormal basis for W, those would be the U's, U1, U2, U3. And those, right, sigma. Okay. So the proof of the theorem. Okay. How did the proof go? We went to T star T, right? Let me go back. What was the first step? We considered this operator T star T, right? Automatically diagonalizable. And we really need its eigenvalues, right? And its eigenvectors to form the first set, V1 through Vn. All right, we can do that, right? We can find the operator T star T and compute its eigenvalues. T star T went from V to V, right? Our V is R2. So that will give us a basis of eigenvectors for R2. Now, you might have figured out already in the previous homework, there was that question there that was asking you that whether a given operator was normal or self-adjoint. There were two questions there, and just trying to compute the adjoint is a mess, right? However, it's much simpler to deal with things like that if you just move everything into a matrix question, right? Because an operator T is self-adjoint or normal if and only if the associated matrix of that in an orthonormal T star T, I'm going to look at the matrix of T star T in an orthonormal basis for V. Okay, what would be an orthonormal basis for V then? Well, just the standard basis, right? The standard basis is orthonormal, so let me start with that. I'm not saying this will be the basis of eigenvectors, right? I'm not saying this will be V1, V2 from the theorem. I'm just starting with an orthonormal basis for R2 in order to find the eigenvalues of T star T. All right. My goal is to find this, right? Because the characteristic polynomial of T star T is the characteristic polynomial of the matrix of T star T in whatever basis I want. I'm choosing this basis. Now, doing anything because T was going from V, which is R2, into R3, right? Beta is just an orthonormal basis for R2. T star is going back to R2, where you have this basis beta. But to talk about a matrix for T, right, I'm trying to split it now because I know that the matrix of the composition is the product of the matrices. But there is no matrix of T star in the basis beta because T star is not going from R2 to R2. There is another orthonormal basis for R3, which is E1, E2, E3, right? Let's call it beta prime. And T star will have a matrix from beta, and T will have a matrix from beta to beta prime, because that's how it goes, right? From R2 to R3 and from R3 to R2. Okay. Those are orthonormal, both of them, so I don't really have to compute two matrices because the adjoint can be pulled out, right, from inside. So all I need to do is to compute one matrix, the matrix of T from beta to beta prime, and multiply it by its adjoint. So this thing here is all I need for now. Let's call it A. All right. So what dimensions does A have? T is going from R2 to R, so the matrix is 3 by 2, right, backwards. 3 rows by 2 columns. The first column is given T of the first vector, which is T of 1, 0, written in the basis beta prime, which is E1, E2, E3, the simplest one possible, right? So T of 1, 0 is what? Where is my operator? Is 1, 1, 1, right? When x1 is 1 and x2 is 0, I get 1, 1, 1. And T of 0, 1 is 0, 1, negative 1. Right? So this is A. This thing here is A star. A star, the matrix is real, so A star is just the transpose. Okay? So what is A star A? It's a 2 by 3 matrix times a 3 by 2 matrix is going to end up being a 2 by 2 matrix. 3, 0, 0, 2. And this is A star A, or the matrix of this operator in the basis beta. All right, we found its matrix, but it's enough, right? We found T star T. We want to find its eigenvalues. What are the eigenvalues? Well, the eigenvalues of T star T are the eigenvalues of that nice matrix, 3, 0, 0, 2, and 2. There are 2 of them. If I arrange them in decreasing order, these are the eigenvalues. And those eigenvalues will give me the basis of eigenvectors, right? How? You take the first one, remember? Take the null space of A minus 3 identity, the basis for this null space. I'll skip this work. You get vector, the basis being 1, 0. Take the second one, compute the eigenspace, so the null space of A minus 2 identity, find the basis, which will be 0, 1. Right, so I'm going back to that proof now. The orthonormal basis V1 through Vn of the first one is given by those eigenvectors. So we're done with the first one. R2, the orthonormal basis for R2 from the theorem, is nothing more than the standard ordered basis, right, in this case. What are the singular values? How do we define them? The square roots of the eigenvalues of t star t. So sigma 1 is the square root of 3. Sigma 2 is the square root of 2, right? So now we need to move everything into the second component, so into the basis, orthonormal basis for the second space, which is R3. The connection is through this. So to define U1, we need to compute T of V1, which will be sigma 1 U1. And T of V2 is sigma 2 U2. All right, what is T of, so those are V1 and V2. Well, we computed that already. It's part of the matrix A. T of V1 is 1, 1, 1. Sigma 1 is the square root of 3, right? So you 1 over the square root of 3 times the vector 1, 1, 1. T of V2 is the second column of A, so is 0, 1, negative 1. Sigma 2 is the square root of 2, U2. So U2 is 1 over the square root of 2 times 0, 1, negative 1. Good? What are we trying to find? We need to find an orthonormal basis for the second space, W, but the second space was R3. But that's pretty much the extent to which our theorem helps us. The SVD gives you two vectors, U1 and U2, because you had two singular values, right? They came from two eigenvalues. Where is the third vector? Well, the theorem doesn't tell anything, so how do you find it? You have two vectors in R3. They are already orthonormal. I need a third one to create a basis. What do I do?
Repeat the question.
So I'm trying to find an orthonormal basis for R3. Okay? I have two vectors in there that are forming an orthonormal set. So they have norm 1, right? They are orthogonal to each other. I'm just trying to find the third vector. Gram-Schmidt. But Gram-Schmidt turns an existing set into an orthogonal set. My set doesn't exist. I have 2 out of 3. I'm trying to add. I know that a linearly independent set will always expand, or an orthonormal set will always expand to an orthonormal basis, but the question now is, all right, so we know this is possible, but how? I mean, how do we actually do that? And if you remember, I mean, there are two ways to think about it. Since it's in all of them, I need a third one. Remember the cross product of two vectors, right? The one that is perpendicular to. Remember how to find the entries? So that's one way. One way would be to say that it has to be orthogonal to both and set up a system of linear equations. Right? You will have a vector ABC such that the inner product with each of them has to be 0, and you solve for ABC. Another way is this. Remember this setting? Right? If you just solve this, compute a determinant of this, you're going to get the cross product between two vectors. It's not going to be orthonormal. Look, notice that I skipped the square root of 3 and the square root of 2. So it's not going to be, not orthonormal, it's not going to be a unit vector. You just divide by its length at the end. All right, so let's see. You expand along the first row, right? I times -2 times -1 plus k times 1. So the vector is -2 plus 1, +1. I want to make it of norm 1. The length is 4 plus 1 plus 1, 6. So square root of 6. So here is the third vector, right? Into here. So we had one vector missing, but there will be situations when, let's say, going from R2 to R3, you only get one singular value, one. That one singular value, we got 2 here, right? But what, if you get 1, you just get one vector into R3, a single U1, and you have to count them. What do you do then? You're missing 2 vectors. Well, you kind of go by guessing a little bit. So you have your first vector U1. Visually, you can come up with one that is orthogonal to it. Right? You can figure out. So for example, so we're done with this example here. But let's say you have a set formed by 2. So let me make it norm 1. But formed by this one, this would be U1. And you need 2 more. How do you find that? So I was saying that I can come up with a vector orthogonal to this U1, like this one. Just the simplest thing possible, right? Just come up with something such that the inner product between that something and the original one is 0. The simpler, the better. Once you have 2 of them, you apply the previous idea, right? You find the third one by taking the cross product and normalizing. Okay. But we'll do more examples next time. As I said, I had to finish 5 minutes earlier to return the pen. So I'll just stop here for today.
You're on a roll. You're on a roll. 10 minutes.
Okay. Hopefully it made some sense. We'll see more examples anyways of this. So I don't expect everything to be crystal clear already on the SVD.